This is an example problem involving Gibbs energy at temperature 298. So the temperature is 298 Kelvin and pH 3. Chymotrypsinogen denatures with a delta G of reaction under standard conditions equal to 30.5 kilojoules per mole, and an enthalpy of reaction under standard conditions of 163 kilojoules per mole. We're also told that the change in the heat capacity upon reaction per mole is 8.36 kilojoules per mole Kelvin. And we want to know the Gibbs energy reaction at 320 Kelvin and pH 3. And so we have some things we actually have to decide. One of them is, how are we going to do this? And we don't have any way of knowing what the Gibbs energy change is when the temperature changes. Oh, but we do know that the Gibbs energy is equal to the enthalpy change minus the temperature times the entropy change. And we know how to change both enthalpy and entropy for temperature changes. And I'll just remind you that the enthalpy at a second temperature minus the enthalpy at another temperature is equal to the integral of Cp dt. And we've solved this already. And the same is true for the entropy, the difference between the changes in the entropy between T1 and T2 is Cp divided by T dt. And we know how to do these two integrals. So if we could figure out what the new enthalpy and the new entropy is, then we should be able to figure out what the Gibbs energy is at a new temperature. So I'll do this in two parts. I'll look at the enthalpy at 320 Kelvin first, and that's equal to the enthalpy under standard conditions plus the integral between 298 Kelvin and 320 Kelvin of the change for the reaction of the heat capacity times dt. And this one I do not need to, the heat capacity change here is not temperature dependent. And so this is the enthalpy of reaction under standard conditions plus the reaction change in the heat capacity times the change in the temperature. And I know both of these values because they're right over here. This is 163 kilojoules per mole plus the change in the heat capacity, 8.36 kilojoules per mole Kelvin. And the total temperature change is 22 Kelvin. And so this turns out to be 183.9 kilojoules per mole. And so the enthalpy at 320 Kelvin is equal to 163 kilojoules per mole plus 183.9 kilojoules per mole, which is equal to 346.9 kilojoules per mole. And now I need some more space on which to write in order to figure out what the entropy change is. So I'll be right back. We're back. I've erased the board, rearranged the information that we knew earlier. So I found the enthalpy of reaction at 320 Kelvin, but now I need the entropy of reaction at 320 Kelvin. And in order to find that, I first need the entropy under standard conditions. But I can get that because I know that the Gibbs energy, I know the enthalpy under standard conditions. The standard temperature is 298 Kelvin, so I can get the entropy under standard conditions. So let's start there. So to find the entropy, I need the Gibbs energy change for the reaction under standard conditions. I'm going to subtract off the enthalpy change for the reaction under standard conditions. And that's equal to T times the change in the reaction, negative T, for the entropy under standard conditions. And so the entropy change for the reaction under standard conditions is the delta G, 30.5 kilojoules per mole, minus 163 kilojoules per mole. And I'm going to divide this by 298 Kelvin. And I need a negative sign in here because I had one here. And this is equal to 133 kilojoules per mole. And then I need to divide that by 298 Kelvin. And so I find out that the entropy change for the reaction is 0.444 kilojoules per mole Kelvin. And that's under standard conditions. Now I can find the entropy at my second temperature knowing how to adjust that. So I'll do that. The entropy for the reaction change at 320 Kelvin. Let me do this. Minus the entropy change under standard conditions is the integral from 298 Kelvin to 320 Kelvin of the reaction change for the heat capacity times dt divided by T. And we know how to do this already. I'm going to just work on this part for a second. This heat capacity change is not temperature dependent, so I don't have to integrate that. I just have to integrate dt over T. So this is the change for the reaction in the heat capacity times the natural logarithm of T2 divided by T1. And when I substitute the values in here, what I get is 8.36 kilojoules per mole times, I'm going to take 320 divided by 298 and then take the natural logarithm of that, and I get 0.0712. And so this piece, the change in the entropy in adjusting for temperature, is 0.595 kilojoules per mole Kelvin, because I'm missing a Kelvin here. And so now I can go back here and find that the reaction change for the entropy at 320 Kelvin is equal to my initial entropy under standard conditions, 0.444 kilojoules per mole Kelvin. And I'm going to add in this value, which is the adjustment for the temperature. And so this entropy of reaction at 320 is actually 1.039 kilojoules per mole Kelvin. And now I can get my Gibbs energy change for the reaction at 320 Kelvin. And this is equal to the enthalpy of the reaction, 346.9 kilojoules per mole. And I'm going to subtract off temperature, 320 Kelvin, times my entropy change, and 1.039 kilojoules per mole Kelvin. I have to make sure that I wind up in the same set of units. And I do. The value of this, I don't know. I ran this through a calculator, and the Gibbs energy for the reaction at 320 Kelvin, all told, is 14.3 kilojoules per mole. Note that the value is positive.